Hi everybody. So apparently we have the same issue as the last week, so don't know what is that, but anyways, we can start till somebody comes to fix it. So hi everybody, welcome to the third session, third lecture on Introduction to Machine Learning. I hope that you could attend yesterday's tutorial because Mohammed was trying to just do some review on linear algebra, which we are going to use quite a lot today. I am going to take you in slow pace, so we are going to just review whatever we need, but just in case anything was unclear at any point, please just let me know. It's okay if you interrupt me. So the idea today is that we want to study principal component analysis. So just a quick recap on what we did up to this point. So we started with the general idea of machine learning. So what machine learning is, so we define it to be a set of data-driven tools that help us to just find out some models which can essentially generalize. And then we talk about the general prescription for any machine learning problem. Three main components: the data, and then the model, which is capturing the pattern, and the final thing was to develop an algorithm, a learning algorithm, which starts from the data we collected and tries to somehow specify a good model. So it's try to tune that model based on the data side that in future it gets generalized. So we talked about the clustering. So it was the first problem we had on the first lecture. The idea was that we had a bunch of data, and what we thought that, okay, this data could be clustered into a bunch of clusters. So you have a bunch of groups. Each data point that you have is going to lie in one of them. And then the question was that how we can specify those clusters. So we went through that. We made a kind of model. So the model was basically looking at the data and giving you back a cluster. And the learning algorithm that we developed, it was basically the k-means clustering, which started from the data points that you had inside your data set. And then it tries to understand a kind of general rule to get one data and then just specify the cluster for you. So this was the idea of k-means clustering. So nothing specific. We start with a bunch of centroids. We say this is the centroid of every cluster, k different clusters, k different centroids. And then anyone who is closer to the centroid is going to belong, any point, any data is going to belong to the cluster to which it is closest. And then to tune those centroids based on the data that we have, we just did this iterative approach of k-means clustering. Just do the cluster assignment and then shift everything to the center of the clusters that you have specified on your data set and repeat this over and over till you don't see any update. And this was the idea. So we talked about this. This was a kind of learning algorithm because it starts from data you have and then it goes and gives you back the model, which is basically those centroids, right? So that was the problem of clustering. We also talked about the density estimation problem last time, right? So what was the problem in the density estimation? So in the density estimation, again, we have a data set, so we collect a bunch of data. And what do we think? What was the kind of pattern we had? Anyone remembering? So we thought that this is coming from a sort of random process, right? And what was we looking for? What was the thing that we were looking for? It was the distribution, right? So what we did, we thought we have, this data, these samples are coming from some random process, and that random process had a sort of distribution. We just specify that distribution. Maybe somebody tells us. Maybe we just assume that because this is a kind of convention. And then that distribution had a specific bunch of parameters which we don't know. And what did we do to find out those unknown parameters? What was the idea? Any candidate to help me? Maximum likelihood. Great, yes. So what we wanted to do, we basically wanted to design one algorithm. It starts from the data that we have, and then it tells us what is the set of good choices for unknowns, right? And then the algorithm that we used was maximum likelihood. And the likelihood basically was that you go and use your assume distribution on the data that you see, and then you compute this probability, and then you search around all possible unknowns, so that this likelihood is maximized. So it somehow made sense because we are looking for the kind of values, kind of unknowns that are best fitting our data, right? And then we discussed the Gaussian maximum likelihood. What was the unknown in Gaussian maximum likelihood? Exactly, mean and covariance matrix, right? The mean vector and covariance matrix, and then we came up with a very simple solution for that. So if you have a bunch of data, you can assume those data are data samples are coming from a Gaussian distribution, and you can compute the mean and covariance matrix of that distribution. This is the whole learning process that you are doing. So that was the problem of the last lecture, and what today we do, we are going to end the unsupervised learning part by doing the final thing, which is the principal component analysis. So what do we do today? We basically try to see whether we can develop some simple algorithm which somehow gives us a solution for the problem of dimensionality reduction. And what is dimensionality reduction? I'm going to explain it today shortly, so no worries about that. So the whole agenda for today is basically this one. So we are going to start with the idea of representing data in a lower dimension. So we get the idea, what do we mean by dimensionality reduction, what is dimensionality reduction, and why maybe we are interested in that. And then we're going to have a short overview on the linear algebra, so you just recap the key notions, and as I said, if you just have any question in between, please just interrupt me and ask the question, because this is very important that you can follow the details. And then and then once you have those things recap, then we can go for the principal component analysis, which is the main thing we want to have today. And then we'll take a look at a few applications of that thing. So this is something that we really use in practice. And you can eventually, after this lecture, try it to just do some compression on data that you have. So, yeah. So then let's start with the motivation. Why do we do dimensionality reduction? And the idea of dimensionality reduction is that you get one data. So your data is, in general, d-dimensional. So I'm showing it here with d, as you can see. So this xn is a vector which contains d different components, and you have lots of them, right? And then what you want to do here, you want to see whether you can find one mapping which gets this vector, the d-dimensional vector x, and then maps it into a smaller dimension, meaning that it's going to return one vector z, and this vector z is going to be k-dimensional, with k being smaller than d. Okay? Do you get the problem of dimensionality reduction? So it's nothing specific, right? So you have a very long vector. You are looking for some solution that gets that vector and give you a shorter vector. But obviously, what you want to do, you don't want to lose any information, right? Because, I mean, if I just want to reduce the dimension, I can drop entries, right? So get the d-dimensional vector, drop d minus k different entries, then you have a k-dimensional vector, right? So it's not only that I'm going to just drop the dimension, I want to preserve information, meaning that if I look at z, I still can understand the same thing that I would understand from x. And this is maybe a bit of vague description, but as we go through the lecture, you're going to get the idea. Okay? So the whole idea is that I get one data, which is eventually very high dimensional, and then I want to see whether I can make it very small without losing information. So one simple example, which is one of the early applications of principal component analysis is to just compress an image. Okay, so you get this image. We talked about this. Any image, you can think of it as a matrix of entries, values, and each value is just showing the intensity of that particular pixel, right? So here, as you can see, you have 200 columns and 300 rows. So in general, if you want to represent this image, this is going to be 60,000 pixels, right? And I can put it into one vector, right? So what is the dimension D here in this example? What is D? So my X is the image, right? X is the image. So it means that X is the image. So this is the first pixel, this is the second pixel, and so on. This is the last pixel. What is D here? 60,000, exactly. So D in this example is 60,000. And what I want to do, I want to just represent it with one Z, which is eventually smaller, say 1,000 pixels. So I just want to have Z1, Z2, till Zk, and this K, which I said should be smaller than D. This is, for instance, 1,000. Clear? Yeah? Now, what I do want, so I start with the 60,000 pixels. I want to, for instance, reduce it to 1,000 pixels. And what do I want? I want that once I have Z, at some point of time, if I want to again draw the same image, I can get back from Z to X, maybe not exactly, but at least approximately, so that when I draw that picture, when I show that picture again, I'm going to see roughly the same thing. Okay? So in that sense, I'm not losing any information, right? So this is something that you already do on your computer, right? You get an image, it could be very high resolution, and you drop the resolution, right? But at the end of the day, you still see the same image, right? You don't zip one, I don't know, cat image and you get a dog. It doesn't happen, right? So you still have the same cat with lower resolution. Clear? So the question is how we can do this. And we want to just maintain the quality, which is the same thing as I said with preserving the information. So if I go on the board, then it would be not recorded, but I need to do it time to time. So, anyways, okay. Now, let's get to one example to see whether such a thing could in general happen. So look at this particular diagram here. So I'm showing in this diagram two-dimensional data. Okay, my data set contains vectors x, and every single vector is two-dimensional, so I can show it in 2D plane, right? So here, every single of those points that you see here, I mean every single of guys here are one data point. And what you see here is that every single point is lying on the line x1 equal by x2. Okay? So every single data point of the data set, when I just draw it, so I get my first data point is here, the second data point is here, the third one is here, and I draw everything inside my data set, I see this one. So here, this guy is the line x2 equals by x1. Yeah? And I see that. Now, if I have one data point, for example, x, and I tell you that the first entry is -1, then what would be the second entry? Given that you have seen this observation, what would be the second entry here? It's again -1, right? Because you see every single point is on the same line, right? So you conclude that most likely this is again -1, right? Now, if I have in general any data point of this data set, and I assume that this data set has this property, everything is lying on the line x1 equal by x2. So if that happens, then do you really need to save this data set with 2 entries? Every single data sample of the data set? No. You can have just one data set, right? Because everything is lying on one line, correct? So everything is lying in a subspace of your original data space. And what is the original data space in this case? The whole 2-dimensional plane, right? So your data, the thing that you see here, your data X, you assume that it belongs to R squared, right? R to power 2. Because your data is 2-dimensional. So any data X that you see, this guy is containing 2 entries. But the fact is that every single point of the data is lying on just one line, right? So it's not really lying on the whole, or it's not covering the whole space, but it's just covering one line of this space, right? So you're just dropping from a high-dimensional space to a lower-dimensional space. And when this is happening, so eventually you don't need both entries of your data, you just need one of them, right? And then you can explain your data. So you can do dimensionality reduction in this case perfectly, right? So if you get from any X, so if you get here, in this case, if I get my X, and then I take my, so Xn, which is one of the data points inside my data set, if I just define Zn to be Xn1, so it means the first entry of Xn, so Xn, this is a vector, and this is of the form Xn1 and Xn2. Since I know that Xn2 is exactly Xn1, so I can just keep this one, right? And this guy is preserving the information, correct? So whenever you want to get back from Zn to Xn, what you're going to do, you're going to get your Zn, and then multiply it with the vector 1, 1, correct? So here you can do the dimensionality reduction. Everything is lying in a lower dimension, so you can just show it with a single scalar, right? So what if I have such a thing now? What if I have a 3-dimensional space, but I do know that every single data point that I'm collecting is lying on one 2-dimensional plane? What's going to happen? Can you do again the dimensionality reduction? How large should be your reduced dimension to do everything perfectly for now? 2, exactly. Because every single point on a 2-dimensional plane, you can just describe it with 2 directions, right? So if you have one plane, you just need 2 vectors to explain that plane in the 3-dimension, right? And the moment that you know what is the exponent or the coefficient of every single direction, then you basically can explain where exactly that data point lies. So every single point, every single of these blue points on this gray plane are supposedly on this 2-dimensional subspace, and I can explain them with simply just 2 numbers, right? So I do not need to save the 3-dimensional vector completely, but I just need to use that 2-dimensional representation. But if I want to know that 2-dimensional representation, what should I know? Any clue? I need to know the directions which are explaining the plane, the 2D plane, right? Correct? So I need to understand them, and I did the same thing here in this 1-dimensional case. So I did know this guy, so I did know this guy. Look at this one. I did know this vector, which was essentially the direction explaining the line on which my data set is lying, right? Since I do know this blue line, I do know that direction, so I basically can write down every single entry in this form, right? Same thing for the 2-dimensional case. So when I go higher dimension for a plane, I need to know two vectors which are exactly orthogonal on each other and lying exactly on the page, on that plane. And once I do know that, then I can explain any point. I can describe any point on this plane, right? So I do need those two orthogonal things, right? And in this case, I can do the dimensionality reduction perfectly, right? But what's going to happen in practice is that you do not have this perfect line, right? So you're going to have your data somehow wiggling around that line, right? So you don't see exactly data line here, but you might see that your data points are somehow like this. So you see your data points something like this, right? So in practice, you're going to see your data points just wiggling around that line. But then, depending on the application that you have, maybe it's enough that you see the projection of that point on the particular line that you have. If I want to just present that data point with one entry, maybe if I see that everything is around that line, so I'm going to get that data point. So I'm going to look at this data point, and then I just project it on the line, which is the main direction everything lying on. And then I take this point as an approximate of this point, right? If I want to just get back to the green point, I cannot exactly do that, but I can get to its projection on the line, which could be potentially very close to the original one, right? This is where I have a bit of loss, but depending on the application, that might be acceptable. Okay? Any questions? Do you get the idea? So, if you got no questions, that's weird why they are not coming.
Your call is being connected.
Just to check they are not getting. Hey, hi there. I talked about 20 minutes ago with your colleague. The microphone, the wireless microphone is not working. I was wondering if you can send someone around. I mean, she said that she has sent someone, but no one showed up.
Oh, okay, sure. So I'll just send it right now. So I just want to know, I mean, if it's like the battery issue or it's like not working. I mean, the microphone is not.
No, it's not a battery issue. It's not working. Apparently, it's not finding the channel.
Okay, I'll send it right now. Send it. Sorry, I'll just send it.
No worries. Okay, so then let's go on with a bit of, I mean, if you got no question, let's just get back to basics, linear algebra. We just do a bit of review. As I said, if anything is weird for you, if anything is not really consistent with what you have in mind, please just let me know. First thing is about the orthogonal base, or orthonormal base. So what is an orthonormal base? So if you are in a d-dimensional space, you have d different vectors, right? And these different vectors have this property that they are orthogonal to each other. What do I mean by being orthogonal to each other? It simply means that their inner product is 0, correct? So, and you have d of them, and once you have those d guys, you can essentially describe the whole d-dimensional space, right? Any point in that d-dimensional space is going to be a superposition of some coefficients multiplied with these bases, right? So this is the definition of one orthonormal base. So as you can see, they are orthogonal to each other. Any two vectors, any ui and uj. Oh, it shouldn't be uj, sorry, typo. So this guy, the first one should be ui, for instance. So any ui and uj, they are going to be orthogonal to each other. It should be 0. And the norm of every single vector is 1. Okay? And the second term normal, which shows up in that term orthonormal is simply indicating that they have norm 1. Okay? So now if you have any point in the d-dimensional space, how you can show it up? You need to just get the corresponding coefficient, multiply it to corresponding u, and then sum them up, right? So if I have some point like x, and this is d-dimensional, this means that this guy belongs to the space R to the power d, then I can write it down as the summation I from 1 to d xi u I. Correct? So these are the principal components of that space. They are orthogonal to each other. And then you just get the corresponding coefficient of this guy, which is its projection on this particular direction, multiply it with that u, and then you sum it up once you have everybody, right? So usually we have vectors in d-dimensional form. And what are every single entry in that vector? Or in other words, what is the basic or classic orthonormal base that we use? The unit vector or the one-hot vector, right? So the classic one is when you consider this matrix U to be the identity matrix, right? So if I set U, matrix U, to be identity matrix, let's think about D equal by 2. So D equals by 2. Then in this case, U is going to be 1, 0, 0, 1, right? And then this is one of the bases. So this is one base. It has norm 1, right? Because 1 squared plus 0 squared is 1, square root is 1, right? This is the second one, right? So this is U2. This guy is U1, right? Correct? This is the classic one. But you don't necessarily need to do that, right? Another one that you can think of is another thing that you can use is to be 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2, 1 over square root of 2. Now, this guy is U1. This guy is U2. Are they orthogonal? This one multiplied with this one is minus half, right? This one multiplied with this one is half, correct? Sum them up. It's 0. They are orthogonal, right? What is the norm? 1 half plus 1 half is 1, and square root is 1. Same thing here, right? So it's an orthonormal base, correct? Now, if you think of this one, what do you see in the two-dimensional space? If I want to just think of the two-dimensional space, when we think of the classic form, you always have this basic form. This is one of them, or maybe I shouldn't show it like this. Maybe still with white. So this is one, which is the vector 1 and 0, right? This is the other one, they are orthogonal, and this is the vector 0 and 1, right? The first column, the second column, right? But now if I think of this one, what is happening? One of them is this guy, so this is U1 now. And the other one is the orthogonal one, which is U2. Right? Everybody's clear? So now if I want to show one point in this two-dimensional space, it depends on the base that I'm using, right? If the point is something like this, let me just get rid of this. Yes. It depends on the base that I'm using. If I'm using this base, then I'm going to just look at this point, then reflect it here. It's going to be, the projection going to be x1, and then I'm going to reflect that one here, it's going to be x2. Say this is the point x, right? And then it's going to be x1 times this guy plus x2 times this guy, right? But I could eventually use the other one. So I could just keep on going like this, and then project this one on this vector, and also compute the projection on the green one, right? Once you have that, then again you can compute with those projections the same point, right? Just you describe it in a rotated base. Clear? Everybody's clear? So this is the classic base, but this is not necessarily the case, right? So U does not need to be the identity matrix. It could be any matrix, and as long as it has the two features that we just talked about, these two features, right? And one key feature of any base is that if you multiply it to any vector, it's not going to change the norm of that vector, right? So it doesn't matter if I show this x in this system or in this system. At the end of the day, the distance of x from the center is the same, right? So you can easily show that if you have those two properties of the base, then the norm of ux for any point x, any vector x that you have, if you multiply it with any u, which is an orthonormal base, then you're going to have basically the same norm, right? The only thing that matrix U can do is that it's going to rotate that point. Okay? Everybody's clear? Any questions? Okay. So if you got the point, then this is eventually what I showed you on the board. So if you have any particular point x and you want to describe it with the given base that you have, you basically just project that point on that new base, and then by just computing the inner product, so this is the projection x and u, and then you multiply it with the corresponding base. And once you do it for every single component that you have in your orthonormal base, then you basically have your vector again represented in the new base. Okay? So that's going to be it. So this is just one recall that when you are, for one-dimensional, it doesn't make sense that much. For two-dimensional case, you do know that we always have two vectors that are orthogonal. If I fix one, the other one is clear, right? And then if you think of d-dimensional, it's always d vectors which are orthogonal to each other, right? You cannot have more than that, obviously. Okay? So that's about the orthonormal base. Now we want to talk about the eigenvalues. Do you have the idea of eigenvalues? What are they? So what is the definition of eigenvalue? First of all, your matrix A should be a d by d square matrix, right? So that is the one, and it's not, the battery is now off, but battery was okay before that, and then it didn't work again. So now, if you have a matrix which is d by d, okay, is a square matrix, then you can define for it eigenvalue and eigenvector. And any pair of lambda vector v are a pair of eigenvalue and eigenvector if you have this particular property. What is the property? You get your matrix, you multiply that matrix to the eigenvector. That eigenvector is going to be exactly the same vector as before, only scaled, right? Everybody's cool with that? So now, one thing here first. What's going to happen? What's going to happen if first of all, this vector v. Say A is d by d. What is the dimension of vector v first? What is it? It's d by 1, right? So this guy is of dimension d. So d-dimensional vector, column vector, right? Now, I get this matrix A, and I multiply it with v, so meaning that I have lots of guys here, right? So different guys here in this matrix A. So I have one bit column here, which is, for instance, A1 till AV, and then I multiply with this vector V, which is V1 till VV. Then I'm going to see lambda V1, lambda V2, and so on to lambda VV, right? So everything got a scale, meaning that if your eigenvector is in one direction, when you apply that matrix on that vector, it's going to stay there, only it's going to go larger or smaller, right? Everybody's clear? So, now, one thing here, if, just look at this guy, so lambda v. Now, if I get this vector v, and then I divide it by some value, say beta, or maybe I divide it by 2. And I make here, again, v divided by 2, and multiply it by nothing, okay, basically. So, is it still correct or not? So I told you AV is lambda v, right? Right? So AV half is again lambda v half, correct? So if lambda is the eigenvalue and v is the eigenvector, any coefficient of v is still an eigenvector, and it doesn't make sense, right? Because then we cannot define it uniquely. It's going to be infinite number of vectors, right? So how we can handle this issue? We just make an argument. We assume that v has specific norm. And usually we think that v has norm 1. Okay? So in addition to this one, you need one extra condition, and that is that norm of v is 1. Everybody's clear why we do that? Once again, if you don't, so it's not working?
It works.
No, it's not working. This is,
I don't know.
No, I did that. I mean, no, it's not. It's usually sound, and then as long as this guy is on, the lecture microphone and the wireless microphone, it should work, but it doesn't work. Last time that happened, and then your colleagues just did some tuning of the channel, I guess, and then it worked.
I'll have to call my supervisor.
Okay, no worries.
Is it okay if you could adjust with the podium mic?
Yeah, I keep doing, but it doesn't get recorded all the time, so that is the issue.
Okay. I'll have a word with my supervisor.
Yeah, okay, no worries. Yeah, thanks.
Sorry.
No, fine. Not your fault. Yeah. So once again, if you have one eigenvector, then if you multiply it with any scalar, it's still satisfying the same property, right? So this means that if v is an eigenvector, then v times anything is still eigenvector. And you don't want that, because in that case, you're going to have infinite number of eigenvectors. So to avoid that, you're going to just decide to have one specific extra constraint, and that constraint that your eigenvector norm is 1. Okay? Now, if you have this matrix A and it is d by d, how many eigenvectors do you have? Any clue? Yeah, go ahead. D different eigenvectors, right? Some of them could be 0, some of them could be the same, but at the end of the day, you have, D different eigenvalues. Some of the eigenvalues could be the same, some of them could be 0. It's all okay, but at the end of the day, you have d eigenvalues and d eigenvectors, right? And two eigenvectors, what kind of property do they have? They are orthogonal. Yeah? So I'm not going to show it here for you. You can take a look at your linear algebra textbooks, but you're going to see there, if any two eigenvectors, you can show that they are orthogonal to each other. Okay? Now, what kind of property you are getting? You're getting two vectors, for instance, in 2 dimension, or if your matrix is d by d, you're getting d different vectors. Each of them has norm 1. This is one property. The other thing is that every pair is orthogonal. So what do they describe? What is that? If you have d different vectors with norm 1, all of them orthogonal to each other? It's a base, exactly. So it's an orthonormal base. So when you have a matrix, that matrix, if you compute the eigenvectors of that matrix, then those eigenvectors are going to describe you an orthonormal base, right? Now, one thing that I would like to just, this is, what the heck? Oh, okay. Yeah, one thing that I would like to show you here is this particular diagram. So, do you have any clue about this diagram and how you can interpret it as the representation of your eigenvectors and eigenvalues? So, as you can see here, I mean, this is the idea that you can, if you want to think about this, say you have one matrix, okay? And this matrix A is 2 by 2, okay? This is going to have two eigenvectors and two different eigenvalues. Now, you're going to get a circle. This circle, if you look at every point of this circle, is in the same distance from the origin, right? Now, if you multiply it with that matrix, and every single point of this circle, you're going to map this into a new shape, correct? So every single point on that circle, so say I have this circle, and then I get every single point of it, so this is going to be one vector x, which is eventually x1, x2. And then what I do, I'm going to multiply this a, x to a. So I'm going to compute a times x, and then I show it again in 2 dimensions, right? So let me call this guy to be y, and then here it's going to be, here it was x2, x1, for instance, and then here is y2, y1. Now, if you do have same eigenvalues, like both eigenvalues are 1, what is going to happen to that circle? What do you see on the y space? So once again, I get this guy, I multiply it to a, I get y, so this point is going to be a new point here, right? And then I do it for every single point, and I'm going to plot that. If they both eigenvalues are the same, then you're going to still see a circle. And do you know why? Because whatever your eigenvector is, it's going to somehow show up like this, right? So there are going to be two vectors orthogonal to each other, right? So these vectors are of this form, and what does the eigenvalue tell you? It's going to tell you how much you squeeze or stretch your shape in that direction of the eigenvector. Since eigenvalues are the same, it says that get the circle, rotate it proportional to the eigenvalue direction, which means that I get this one and rotate it, but do not do any change in any direction, right? So it's going to remain a circle, correct? But what's going to happen if I have a larger eigenvalue for this one and I have a smaller for this one? What's going to happen? It's going to get exactly stretched in this direction. So you're going to see an ellipse, right? And the rotation, the orientation of that ellipse is proportional to the eigenvectors. The one which has larger eigenvalue is going to have larger radius. The one which has a smaller eigenvalue is going to have smaller radius. Clear? So this is the way, I mean, this is the reason that we call it eigenvalue and eigenvector, because they are essentially describing the whole mapping being done by the matrix. By the way, do you know what does the word eigen mean? It's out of the lecture, so you can't answer. Do you know what does eigen mean? It's a German word. It means your own. You know? Really, in German, they say eigene Ding, like your own thing, right? So eigenvector, Hilbert first time called this eigen. Hilbert, the great mathematician. This is the own thing of the matrix. Okay. So once you have the eigenvalue and eigenvector, you can basically know what does the matrix do. So I hope this was clear. I don't want to spend more time on that, but I hope this was clear for you. What does eigenvalue and eigenvector mean? One key feature that I'm going to use today is this guy. Okay? And that is the decomposition that we are going to do. Okay? So what is this decomposition? Let me show you this, and you're going to see how easy this decomposition can be shown. So I could have one matrix A, and say I do know all the eigenvectors of this guy. Okay? Now, I am going to multiply A to every single eigenvector. So I multiply to AB1, AB2, and so on till ABD. Correct? Okay. So first of all, what is the dimension of this AB once again? A is d by d, B is d by 1, so it's going to be d by 1 again, right? So you have d different values here, right? So if I put it in this form, this is still a d by d matrix, right? But since they are eigenvectors, what do you see then? What should it be? AB1 is lambda 1 b1, right? So it's corresponding eigenvalue lambda 1 times eigenvector b1, right? So you can write the second one, lambda 2 b2, and so on till lambda d bb, right? Okay? Everybody's clear? Now, once I have written this one, this is basically the first line that I have written for you. And then the second line is this decomposition. Do you see this decomposition or not? So I put all of those eigenvalues on the diagonal and then multiply them with that matrix. It's going to end up the same thing. Everybody's clear? Yeah? Just take a few seconds, see whether you see that what we have in line 1, which is the same thing on the board, is going to be the one in line 2. When you get that diagonal matrix, every diagonal term is going to get multiplied with the corresponding vector, column vector, right? Okay, so now that you have this, one thing that I can say, let me call this whole thing. So I told you that this is going to be d1 till dd multiplied with lambda 1 till lambda d. So everything else here is 0. It's a diagonal matrix d by d. This is the matrix containing all your eigenvectors, right? So let me call this guy to be matrix V. What is the dimension of V? Number of rows is D. Number of columns? It's a D by D matrix still, right? So let me call this guy also to be matrix lambda. So still, lambda is also D by D, correct? Now, this guy on the other side, this one, I can take this A out of the whole equation, right? So I can put A here, and it's still going to be the same thing, right? So A is going to get multiplied with every single column, right? So this is again V, matrix V. So what do you conclude? We conclude that, sorry, I just write it shortly here. So we conclude that A V equals by V lambda. Correct? A V equals by V lambda. Correct? This is a matrix, not a vector. So here. Now, V is an orthonormal base, right? Meaning that if I multiply this guy with its own transpose, what can happen? The identity matrix, right? So every single column here, I mean this guy and this guy and this guy, all of them are orthogonal. So if I multiply it with this transpose, this guy is getting multiplied to itself, it's going to be 1. This guy multiplied with any other guy is going to be 0. So if I multiply both sides from right by V transpose, what's going to happen? Here you're going to have V transpose. Here you're going to have V transpose. And this V transpose is simply identity matrix, right? So you can always write down any matrix A in this form as long as you do know the eigenvalue and eigenvectors, right? So you're going to have this decomposition, which we call it eigendecomposition of the matrix. So every single column in that vector matrix V is a eigenvector, and then every single diagonal entry in lambda is going to be the corresponding eigenvalue, and then V transpose is basically the transpose version of V, which if you multiply it to V itself, it's going to end up being identity matrix. Everybody's cool about that? Yes? So this is eigendecomposition. It exists as long as your matrix is square, right? And you do know the eigenvalues and eigenvectors, you can always write it down. Yeah? And I guess Muhammad yesterday, he tried it on Python for you for some numerical examples. Okay, so just a few features of these eigenvalues and eigenvectors. So you can determine the determinant always from the eigenvalues, just multiply all of those eigenvalues to each other. And now you can compute the trace. Some of the eigenvalues is the trace. And one key other point is that if you have a positive semi-definite matrix, you're going to see that all the eigenvalues are positive or zero. They are non-negative. Okay? And you don't really need to confuse yourself about this particular definition. I mean, you can check it up later. But one particular example, which we are interested today on, is when your matrix A is written in the form of X transpose. And X could be any matrix. It doesn't need to be a square anymore. Yeah? Okay? So if X is any matrix, say it has 5 rows, 1,000 columns, okay? Once you multiply it with its own transpose, what's going to be the product? If X is having 5 rows and any, say, 1,000 columns, what is X, this matrix A? X transpose. What is the dimension of this guy? It's always 5 by 5, right? Because this is 5 by 1,000, this is 1,000 by 5. Those 1,000 going to get inner producted, just disappear, and then you're going to end up with 5 by 5, right? Everybody's clear? And this matrix is positive definite. You can try it by definition, you're going to show it. I mean, positive semi-definite, of course. Okay? And we're going to use this. So if you have such a matrix and you compute the eigenvalues, they're going to be, all of them going to be non-negative, right? They're either 0 or positive. And this is a key point that we use today. So that being said, any question on that? So everybody has a kind of refreshment on the linear algebra? Cool, great. So let's go on with the idea of dimensionality reduction. So what was the problem that we wanted to do? We wanted to just reduce the dimension, right? Meaning that if I have one particular vector xn, I want to just represent it with a few components, right? And let's try with the most simple case, the one which we had here, where I just want to show the whole vector with one single number, okay? So if I want to do that, I can write down my vector x in the form of that single number, as you can see here, Zn. This is just a scalar. Multiply with one vector u. Okay? Let's think of it for the moment. Okay? Just forget about that hat here and also the mu here. So if I write it down in this form, if x is in d dimensions, what is the dimension of u? It's again d-dimensional, right? So I have one vector d-dimensional u, and then I just look for one number z that I multiply into this guy, and I get my x. Do I necessarily find that? No, I cannot necessarily find that, right? So what I can do instead, I can just say, okay, maybe I can find some vector which is close to the original vector I am looking for. So this is why I am writing down x hat here. So x hat n is not necessarily the same thing as you started with. It's not exactly the sample you had. So x hat n and xn are two different things. Okay? And now, I put also one mu here. And the reason is that I am thinking of the case where I also could have bias. What do I mean by bias? So let's do it here. So say I have this case where I have my points lying on this line. So I have this line. Okay? This is the line that I have. So what I do know is that this particular direction is the direction of u. And still, think of the dummy example we had. Every single data point is lying on this line. Okay? If I want to really use this u to show that one, what should I do? How can I write it down? So say I have this point x here. So this point x, I need to first get from the origin to this point, right? Correct? So I'm going to start from 0, 0, and I go up, I get to that point. Now this is the point which is mu. This is the point I start from. And once I'm at mu, I just need to know the value of z. So this is going to be my z value. This is z. And I just need to multiply that z with the direction u to get exactly to the point x, correct? So this mu is going to be 0 if I knew that this line is passing through the origin, right? But when the line is not passing through that, when it has a sort of bias, I eventually need to have some bias, right? So I can, at the end of the day, write this guy to be mu, the bias, plus some z, which is a number, it's not a vector anymore. And then I multiply it with the direction u, which is a vector, right? So this is a thing that you have in this line. With one difference that I just write down here x hat, because I assume that the original point is, for instance, here, x, and then I am just estimating it with some x hat, right? So it is not the exact point that you had originally, it's just the approximation. Clear? So this is going to be the representation that we have or we are looking for, right? So when we are doing the dimensionality reduction, we are basically looking for some z, which are actually we are looking for some u and mu, which is going to help us compute one good approximate of the original point, right? But that z is just one number. X itself could be a very high dimensional vector, right? Everybody's clear? Any questions? And I'm going to just consider this u again to be norm 1, unit norm. And the reason is because it's just a direction. I don't want it to scale anything. Okay? Any scaling, I'm going to show it in z. Everybody's cool? Okay, cool. So if everybody's cool, then just this is the same diagram I showed on the board. So here I basically have my x. This is the direction u. You can see it here. And then this is the point mu. So I was somewhere in the region. Then I got, so look at it here again. I'm at the origin. I just moved to the point mu. And then from mu, I can start computing. So mu, I multiplied with zn. I'm going to get into this point. This is the approximate. So this is x hat n, which is the approximate of xn, right? Everybody's clear? Now, if this is the approximate, and say that I give you u and mu, can you tell me how you can compute z for that point? So you have it in the slide. So get back to this guy. This is mu, right? If I wanted to talk about the vector x, I just draw it slightly here. Oh, no. this is the vector x, correct? This is vector x, correct? And this particular one, so this, okay, this is a mess now, but do I have any other color? I think I have just 4, and I've used all of them. So this one, or this one, oh no, this one, this way. This is your x minus mu. Do you see it or not? So x here, this guy, this is the point that you have, minus your origin, or your bias, sorry. It's going to be x minus mu. Once you have this, how do you compute z, the value, this distance? How do you compute z? You just project this one on u, correct? So again, look at it here. Mu is the start point. X is the absolute vector of your data point, right? And then you connect this mu to x, so this is going to be the vector x minus mu, correct? And then you know the direction u, so you only need to just project it on u. And if you want to compute the projection, you basically need to compute the inner product, right? So your Zn, the value of this Zn, once you have u and mu is specified. You just get any data point, you just subtract it from the bias, you compute the inner product with u, and then you're going to get your Zn. Everybody's clear? Any questions? Okay, so if you got no question, then let's just extend our idea a bit more. Say we have 2 vectors, u1 and u2. In other words, what I want to do is to just think about that plane we talked about in the 3 dimensions. So I just want to look at 2 vectors, u1 and u2, and any vector that I have, I'm going to project them on those 2 directions, and then I take those projections as my reduced dimensionality, right? So any 3-dimensional point is now shown by 2-dimensional points. So, or in general, if I have a d-dimensional point x in d-dimensional space, then I have 2 vectors, u1 and u2. I, of course, do have one bias because not necessarily my plane is passing through the origin. And the thing that I'm going to do is that I'm going to multiply every single z with its corresponding direction, add it up to the bias. This is going to give me 1 point on the plane. If my data is really on the plane, then this is the exact data that I'm looking for. If the data is not on the plane, is somewhere above the plane, it's going to be 1 approximation. And that approximation is simply the projection of that point on the plane, right? Everybody's clear? So, again, if you want to compute z1 and z2, you basically need to just think of 2 directions. So one of them is u1, and then you just project your x minus mu on that u1 direction. This is going to give you z1, and same thing going to happen for the other direction, right? Clear? Any questions? Okay. Great. So if you got no question, then let me just simplify that or represent it more compactly. So if I just think of my z, which is my reduced dimensionality, in this case is 2-dimensional, right? So it is a vector of 2 entries. And this vector of 2 entries, I can just put them next to each other, zn1, zn2. So these are the vectors that, or entries that I do have. So the first one is going to be u1 transpose times x minus mu. The second one is the second direction, inner product with x minus mu. I can take this x minus mu out of the whole product, right? It's not going to harm anything. So I'm going to put it here, and then I have this particular matrix, right? It has 2 different rows, and in general, d different columns, right? Now, these u1 and u2, I told you they are bases in the reduced dimension, reduced space. So I can put them next to each other. So u1, u2, I define it to be matrix U, the capital U. And this matrix U, what I have here in the first line, this is basically its transpose, right? So what I can say the vector Zn, it means all the reduced dimensionalities that I do have, that vector which contains a smaller dimension, I can always write it down in form of this matrix U transpose times X minus mu, right? So it's the same thing as we did with one single representation, one single scalar representation. Now you can do it in 2 dimensions, right? And instead of matrix vector U, now you have a matrix U, and everything is as before, right? Okay? So this is going to be the expression for Z. So if you want to compute Z, you basically need to multiply U transpose with your X, the unbiased. This is what I call it unbiased data. So I'm going to get the data. I just subtract it from the biased term mu. And then once I have this, I have my Z. And if I want to get back to my data, it's going to be simply U times Z plus mu, which I'm going to show you in the next slides. Okay? Any questions? I mean, it's really hard for me to stop here and talk. And obviously, I mean, I have a bit of confusion. I don't know if it's too obvious for you or it's too boring for you or tiring for you. So it would be very appreciated if you just tell me whether it's clear or not. Everybody's cool? I mean, if you have questions, just let me know. Okay, apparently everybody's cool. Okay, great. So now, let me now just get to this. So let me just write down this one. So the one which we already expressed. I mean, I'm going to show it in another slide, but I just want to keep it here. So if I want to compute Zn, if you give me Xn, for the moment you assume that U and mu are given. So say U and mu are given. Now, if I want to compute any Z, so this is the guy which has reduced dimension, then I am going to write it down as U transpose times X minus mu, correct? So this is the same, I mean, this is the data that I have. I subtract it from the bias, I multiply it with matrix U, and then it's going to give me Z. This guy has lower dimension, right? So in the example I showed you, it was 2-dimensional, right? But this X could be potentially very large, 1,000 dimensions, right? And this matrix has 2 rows, 1,000 columns. So once you multiply, you get only 2 numbers here, right? So this is one thing. And now if I want to get back to my data X, then I can write it down to be U times that guy Z. And then I can add up mu to it, right? Correct? So Z is going to get multiplied with U. This is 2-dimensional. It has 2 entries. But this matrix is 1,000 rows, 2 columns. So once you multiply it, then you're going to get 1,000-dimensional vector, right? And then you add it up with this bias, you're going to get your data. This happens when everything perfectly lies in that 2-dimensional plane. When it's not the case, I'm going to put X hat here, right? So this is then an approximate of your original data point. Clear? Now, before going on with that, let's just look at this matrix U, see what kind of properties it has. And for the moment, let's still keep on with this case of 2-dimensional space, okay? So assume that my matrix U has only 2 column vectors, U1 and U2, okay? Since U1 and U2, I told you they are both bases, so they are having magnitude or norm 1, and they are also orthogonal to each other. If I just compute U transpose U, what's going to happen? U transpose U, you can write it down. I mean, it's going to be U, we said, matrix U. In this case, it was U1, U2, right? So if you transpose it, it's going to be U transpose, U1 transpose, U2 transpose, right? So let me just compute this for U1s. So if I want to compute U transpose U, it's going to be U1 transpose, U2 transpose, and then you multiply it with U1, U2. Okay? What's going to happen? U1 is getting multiplied with this one, right? U1 again gets multiplied with this one, U2 with this one, U2 with this one, right? So you're going to see this matrix you have in the slide, right? And now, these norms, I mean the first entry in the diagonal, the second entry, both diagonal entries, they are norm of U, which are 1, right? We said they are 1. And the inner product is 0, so this is simply the identity matrix. And the dimension of the identity matrix is 2 by 2. Clear? So this has this property of the orthogonal base, but there is one key difference here that you should pay very much attention to, and that is that you are getting this U, which is rectangular in general. So it has D different rows, 2 columns, right? And then when you multiply it, you end up with I of dimension 2. You're not ending up with any D by D matrix anymore, right? So you can think of it as the same V we had there, but you have dropped a bunch of the columns, right? So you just kept a few of them. Clear? In this particular example, 2 of them. Everybody's cool? Okay, great. So now, this is basically what I wrote here for you. I mean, I have it more detailed in this slide. So if I want to get back to my data x hat, then what I do eventually do, I'm going to get every single z that I have in the lower dimensional projection or lower dimensional transform, and then multiply it to the corresponding direction uk, and then sum it up. In the example we had in the previous slide, k was 2, but now if we think of a general k, which is smaller than the original dimension of our data, then we're going to have these k different terms. For instance, this k is 10, but the original data size is 1000. So it's still much smaller than your original data dimension. So you have 10 different z's in that case, and then you multiply every single one with the corresponding u, right? And you just add it up. So just a second. So, and then you can simply write it down again as before. So you can just write it down as this different vectors multiply with the z, and then you can write it down finally in this form, which is the form I showed you here, right? And of course, if you want to get back to your z, again, you just use the same formula. So the same formula we just derived for the 2-dimensional case is valid for any k-dimensional case. Yes?
Is it wrong to say that U represents basically an eigenvector, right? It's a component of the orthogonal basis?
An orthogonal basis, but the question is eigenvectors of what basis? So you got it totally right. So up to this point, you're totally right.
Yeah, so if that's the case, then where do you derive the bias from?
The bias, because I mean, I showed you the circle here, right?
Yeah.
But I could put circle here, right?
Okay.
No? So if I want, I mean, say this is the circle, right? And now I don't want to map it to an ellipse here, but I want to map it to an ellipse here. What should I do?
That's the bias, yeah.
Just a bias, right?
But where do you, so given an additional matrix,
Okay.
you can decompose the matrix, you know, to acquire its eigenvectors and values respectively.
Okay.
How do you derive the bias out of the additional matrix
No, you cannot do that.
You can.
You cannot. I mean, look at this line here in this case. You can never represent any point on this line as one coefficient times x, right? So say this is y, this is x, okay? Or maybe I just clean it up here. Okay, this is still here. So say this is y, this is x, okay? If the line is something like this, any point here, which is y, if I call it y, you can never write it down as one weight times x. This is not happening, right? Maybe you fix it for this one, but the weight is going to change for the next one, right?
Yeah.
Yeah? So the only way you can represent it is to just represent it as wx plus some fixed guy, and that fixed guy is basically this one in this part.
Yeah.
Right?
But yeah, just asking the break. It's just, I don't know.
If you have a matrix, that matrix is basically that weight, the W, in higher dimension. So whatever it does, it can reshape your specific region you're looking in. It can just rotate it, but it can never shift it, right? If you want to shift it as well, then you need the bias. simple thing. You have your center, okay, 0. Whatever your matrix is, your matrix times 0 is always 0, right? So you can never map this 0 to any other point by a matrix. You need a basis, right? Yeah, basis is just shifting everything.
So
That's
there's
not an issue.
Yeah, there's not always a bias though, right? Like sometimes you're just given a matrix like A, and then there is just no bias associated with it.
No, the bias has nothing to do with the matrix.
Yeah,
They are totally independent. We are going to derive the bias independently, and then you're going to see that you can forget about this.
Yeah, that's what I mean. Just something unrelated at the end.
Yeah, exactly. You're going to see that.
Okay.
So, moral of the story, wherever you have, I mean, the whole dimensionality reduction problem, as long as we think about everything linearly as we are doing right now, you can write it down in this form. So you have your lower dimension, which you can write it down as U transpose unbiased data point. And then you can get back to your approximative data point by using the same matrix U multiplied by Z, which is your reduced dimension, plus the bias, okay? So this is what we call it the dimensionality reduction story or problem. And then one thing, as I said before, so this matrix U, this is going to be like in this particular example, what is the dimension of U? Just remember that every single data point was d-dimensional. So what is the dimension of matrix U here? How many rows does it have? What is the dimension of every single vector U? Is D, is in the same space as your data, right? So how many rows does your matrix have? Number of rows, please. I sincerely ask you to help me about that. What is this number of rows? If you don't see it, then this means that what I said was nonsense. What is the number of rows for U? U1, what is the dimension of U1? Your data is d-dimensional. What is the dimension of U1? It's d, right? So U1, U2 till UK, all of them are d-dimensional. Now, how many rows do you have? D. How many columns do you have? K. So you're going to have d by k matrix, right? Now, one thing is that if I get this d by k matrix, so U now is d by k. U is now d by k. And now, if you multiply U transpose by U, what is this guy? K by d, right? This guy is d by k. This one is k by k. And what is k in comparison with d? Is it larger or smaller? Smaller, right? So it's smaller, you're going to have this identity matrix, right? And this is because every single column is orthogonal. But one thing that is very important that you pay attention, if you get U and you multiply with U transpose, you cannot get to the identity matrix. And I hope that you see it. If not, just please redo this at home. Just write yourself one example. Say K is 2, D is 3. Try it, and you're going to see. This is not going to happen. Okay? D is in general larger, and you do not have that much orthogonal vectors, right? You have only k orthogonal vectors. So only you can end up with the smaller dimension identity. You are not ending up with the larger dimension identity. Okay? Everybody's clear? So as I said, this U is a part of the orthonormal base, right? It's not the complete base. Some of those components, principal components of that base, are left, which in this particular case is d minus k different of them, right? Okay? Everybody sees what I'm saying? So one example, say d is 3, so your data is in 3-dimensional space. How many bases do you have in 3-dimensional space? 3, right? And what is the dimension of U? Say U is 2 by 3, K is 2, okay? So matrix U is 3 rows, 2 columns, right? So these 2 columns are 2 of your bases. The third one is missing, right? And why it's missing? Because you didn't want it. You wanted to just get 2-dimensional Z, right? So don't do the mistake. That U transpose is not going to be the identity matrix, yeah? Because if that would have happened, then everything was solved, right? So, okay, great. So if this is the case, then the whole problem can be formulated in this form. So we want to do dimensionality reduction. We basically are looking for some U and vector mu such that it does this for us. It gets some X, which is in D-dimensional space, and then computes the low-dimensional space, K-dimensional space in this particular case, K-dimensional space Z, in this form, with this linear transform, right? And we usually call this Z the latent variable. So X is the original variable that you have, and then the latent representation of that variable is Z, which is just getting reduced in dimension. Yeah? Okay? Everybody's clear? This is dimensionality reduction. And what do we want alongside with this dimensionality reduction is the capability to reconstruct our data. So data reconstruction, basically we get the same U multiplied with Z. So if we have that U, again, that is D by K. So when you multiply it to the reduced dimension K, it's going to be a D by 1 vector. And then you add it up with the bias, you're going to get back to one vector, X hat. And we hope that this X hat contains as much information as possible about X. In the ideal world, it's exactly X itself. If it is not the case, then it's very close to X. Okay? Everybody's clear? Any questions? No questions? Great. So if you got no questions, so yeah, maybe we could have, so it's 34 now, maybe we have 6 minutes break and then we just continue, okay? No, I think you justify your answer as dot trivial, and then which data you passed as the input. So it's 2 questions. Yeah, no, but yeah, you give the data set only, yeah, but it doesn't have anything with the previous.
看这人傻眼。
The data set, that's right? Yes. Okay. Yes, exactly. So
感觉是从床爬起来。
yeah. But if you get back to so it also asks you to change K, right? From 2 to 7. And then it was what you should be like justify
哎，
what's going to happen. Which is the thing where you get smaller data, right?
这件就是毛衣也是 UT 的，还是有好看的衣服的。在哪里买？
一般会今天早上上课的时候，
咱不就在这上，在那个那边上，是那一个不可。
所有的周边
好用吗？它有那个运动的。他们那个也还行吧，
他那个应该
特色。
时间很甜。
对。啊，好烦啊！99的。重要好像是。要不要回去？
But what you showed me, that was not the most important. That was the ingredient, the illustration of the operation. Yeah, I agree, which is the case in both of these. But when the maximum value is so you should go and
一会吗？你没有时间了，还要上课。
1秒窜出去。
So, shall we go on? So, now, let's then look at the dimensionality reduction problem as a kind of learning task. So, if you have a learning task, we have three major components, right? The first one is data, the second one is the model, the third one is the algorithm, which is just getting the data, specifying the model, right? So what is the data here is a bunch of high-dimensional vectors you're collecting. So those vector x, n are in the d-dimensional space, very high-dimensional. Then your model is basically for this particular formulation we had here. This guy is going to be your model. It's going to get your z out of x using u and mu, right? So once you have u and mu, you're going to just project the unbiased data to a very lower dimension. Now, if you want to do that, what do you need to know? What are the components missing or unknowns in this model? What are the unknowns? So the mapping is from x to z, right? What is unknown? What is left unknown here? U and mu, right? If I find u and mu, then everything is over, right? Then I can do the mapping. So basically what I'm looking for some, say, u star and mu star, which are good choices of u and mu that they do this job for me, right? But what does good mean? And we are going to talk about this, okay? Like what we did in clustering or in the distribution learning, right? We need to define some sort of metric which we feel like, okay, if this metric is very well optimized, then we basically have a very good model, okay? So, now the key question is that how we can define the good choice of u and mu. I mean, intuitively, when we started to talk about this, we said that we want to preserve information, meaning that we want to just lose as less information as possible. So let's try to just formulate this guy. So say that I have this u and mu, and then I computed this latent space z. So I have this u and mu as you see in the model. So u and mu are fixed. Once I have it, I get the latent space z. And as I told you, if I want to reconstruct with this model, I reconstruct x hat, which is a kind of approximate of the true x, in this form, right? I'm going to get z multiplied with u, added up with the bias. I'm going to end up with this x hat, right? Now, this x hat is an approximate of x. And what is your intuition? How do you call this a good approximation? It should be not that different from that guy, right? Like in the ideal world, if x hat was exactly x, you would have been happy, right? This would have been the best thing you could have. So if x hat is exactly x, it means that if you just compute the distance and say the distance is Euclidean distance, okay? So you get your x hat, you subtract it from x, you compute the norm. This is Euclidean distance. This guy should be 0, right? In the ideal form. You do know that this is not going to happen necessarily because you're not sure whether your data is really on the lower dimension, spanning on the lower dimensional subspace. You don't really know that your data is really lying on one line. It could be around the line, right? And in that case, your approximation could not be exact. Correct? So, if your approximation is exact, this guy is going to be 0. But when it's not exact, then you would say, okay, this is going to be approximately 0. And what does approximate mean here? It means that you just try to make it as small as possible, right? You just try to find x hat in a way that this is as small as possible in distance from x, okay? So now, if I wanted to do it in the ideal world, what should I do? I should look for every x possible in my data, and then I compute this distance for every single of them, and I try to make it very small for every single of them. But this is not really happening in practice because, first of all, I don't have access to all the data. I just have access to data set, which is containing some samples of the regional data. So remember, data set is samples of the regional data, right? So your data could be, theoretically infinite in dimension, in size, but you just have a finite number of samples from it, right? So you don't have access to the whole data, and in many examples, even if you can describe it, you cannot really check that approximation for all of them. So the good approach is that, again, like what we did in the clustering and also in the distribution learning, we just look for the data that we have in the data set. So we take those samples and try to make this approximation as close as possible to 0 distance from the true sample for all of them. What does it mean? It means that I go now after every single xn inside my data set. I try to just use my linear transform to compute the lower dimension latent representation. And then I get that latent representation. I again reconstruct my data. I'm going to end up with x hat n, right? And then I try to just find the distance between x hat n and the true xn. And I try to make it as small as possible, right? For every single guy that is inside data set. So how can I do this? I can easily define, again, something like risk that we had before. So you're going to compute this distance for every single point inside your data set. So every single point that you have, you compute the latent, you take it back, reconstruct the point, and then you look at the difference, right? And you do it for every single guy inside your data set. You add them up, or you average them. Huh? And then you try to minimize this term. I mean, when this guy is minimized, this means that every single of them is in a very tiny distance from the original one, meaning that you are doing fine, at least on the data that you have inside your data set. Correct? Everybody's clear what we are doing? So it's basically the same thing we did in the clustering and we did in the maximum likelihood approach. We're going to talk more concretely about this when we start with the supervised learning as well. Okay? So that's it. So I'm going to minimize this guy. And by the way, if you just want to confirm, validate my claim, you can simply see that if this term J, this distortion or risk, if this guy is 0, what does it mean? When it's 0, every single term inside the summation is non-negative, right? So every single of these norms is either 0 or positive, right? When it's 0, it means that every single of them is 0, right? Meaning that for every single data point that you have, you're exactly getting the perfect reconstruction, right? So that is fine in the ultimate form, because this J could be at least 0. It can never be negative, right? So if you minimize it and everything is working perfectly, then J is going to be 0, and then this means that for every single data that you have inside your data set, you have found your U and mu psi that once you compute the latent space and you get back by reconstruction, you're going to end up exactly at your original data, right? So you have done 0 error compression. Yeah? It's a perfect thing. But in practice, it's not going to be exactly 0. It's going to be somewhere close to 0. Okay? And then that's still okay, right? You have a bit of error, but this is the minimum error you could get. Okay? Now, if you accept what I explained about the approach for finding or training your model, then the perfect or optimal choice of your model is going to be the one which is minimizing this J term, this distortion term, right? Everybody's clear? So the perfect choice of U and mu is the one which is just minimizing this term, and we eventually want to solve this optimization problem. Okay? Now, one thing, again, I mean, if we wanted to do this in a classic form, we just compute the gradient, set it to be 0, and then everything was over. But I'm not doing this because for this simple problem, we can do it easily, more easily. We are going to do that later when we get to supervised learning, because there is no, I mean, simple behavior anymore. So you cannot compute that optimal U and mu anymore analytically. Yeah? But in this particular case, we can. So again, I'm not going to use gradient descent, things like that. We're going to use it quite later. Yeah? Right now, I'm going to solve this problem, but I'm not using gradient. I'm just using some intuitive illustration. Okay? Any question? Everybody's clear? Okay, great. So if you got the idea, let's start with the simple term. And that simple term is the term mu. Okay? That mu, it turns out to be, I mean, you don't really need to think of U when you are designing mu. And how it comes, let's just look at this particular expression. So this guy J is the distortion that I had, right? Okay? This J here, you see the mouse here, right? Okay. This J is the distortion that I have, right? And I said this is the summation of these different differences, right? Okay. So first of all, let's write down x hat n, in terms of its latent representation. So this guy, oh no. So this guy here, this is the one in terms of latent representation. Look at the board. So x hat is u, z plus mu, correct? So I'm going to replace x hat with its reconstruction term, right? So if I have the latent representation Zn, then I multiply Zn with U and then add it up to the bias. This is going to be my X hat, right? Clear? Now, one thing, how do I compute Zn? I can again write it down in terms of U and mu and X, right? Look at it here. How can I write Zn? Zn is U transpose X minus mu, correct? So I'm going to replace it again here. So this Zn that you see here, this Zn guy, I'm going to replace it with this term. This is the term for Zn, correct? Everybody's clear? Right? So I wrote this down. Now look at this mu minus xn. Can I write it down minus xn minus mu? Just multiply everything with minus, right? So if you look at the board, then if you look at the board, I'm just looking in this line too, right? And then this distortion J, this is 1 over n, summation up. So I'm computing the norm. Here is U transpose, right? Yeah, U transpose I have. And then I have xn minus mu. Then it is plus mu minus xn. Okay? Right? So what I'm going to do, I'm going to just remove this plus. I write it minus, and then it's going to be minus plus. Correct? It's the same thing, right? So xn minus mu, xn minus mu. Correct? So let me just sort it out. So it's going to be xn minus mu. Now, if I take out this xn minus mu, what's going to happen? So I'm going to keep xn minus mu here. What should be here, the thing that is getting multiplied with this one? So U transpose is here, and then I can subtract it from I, and this I is exactly d-dimensional. Is it correct or not? U transpose multiplied with this one is this term, right? Minus I transpose, I multiplied with this one is going to be this time, correct? Everybody agrees? Right? So, same thing we did on the board. So we can just factor out U transpose and I, and this is going to be this term, right? Everybody's clear? Any questions? So now, let me just call this matrix A to be that term which is getting multiplied. So A is this guy. This is A. What I'm computing is this one, right? So I can remove the whole thing here, and I say that I am computing A. And one question, does A depend on mu? Does A depend on mu? Does it depend on mu? Not U, mu. That vector mu, the bias. Does it depend on that? Look at the term for A. It's U minus I, right? There is no mu there, so it does not depend on mu, right? It's something totally independent of mu, correct? Okay. Now, what I have as the loss here, or as the distortion J, is basically A times X, the data that I have, minus A times mu, and this mu is my bias, correct? Now, if I now define this A times X to be a new vector, say Y, okay? And also I call A mu to be another vector, A. Then this loss that I have, this distortion that I have here, is basically this term, right? So this average of all these Y minus A's, right? Everybody agrees? Everybody's clear? Yeah? Question? Yes?
I have a question, but about you.
About
About you.
About you, yes?
Like, on the previous slide, when we talk about you, is that the same as when we talk about eigenvalue decomposition, where A is equal to B, I don't know, it's called D delta V?
V lambda V. No, it's not the same thing. It has a part of it. It doesn't have all of it.
But is D and U not the same thing, both representing the eigenvectors, though?
Sorry?
Like, what's the difference between you, like D and U then? If they're both
U
representing
is, you're going to see how you can relate that U to eigenvectors. But one question that you should write down, think about, eigenvector of what?
the initial matrix,
What is the matrix?
maybe the init or whatever data set's in question?
It's not the one. So we're going to find out how you can find that U in terms of eigenvalue of something. It's going to be eigenvalue of the sample covariance.
Oh,
Okay.
okay, so U is separate.
It is separate, right?
So the V though is the values of the initial data set, though, right?
V? We don't have V here.
When we had before, when we have A is equal to
Yeah. I mean, if you have any matrix, you can always find V and lambda. This is correct, right?
Yeah.
But you need to find the main matrix which relates to U. And once you find that, then you're going to put the columns of U to be eigenvectors of some eigenvectors of that kind.
And we just haven't gotten to it.
Sorry?
Like, 'cause we haven't derived U yet.
No, we haven't done this yet. We are going to do it quite soon. I mean,
But is it just a bias?
it's just a bias. So I wanted to get rid of that in here.
Okay.
Okay. So now look at this term. This term, okay? And forget about all of this bias and other things, okay? You have a bunch of y's, okay? You have a bunch of vector y's, y1, y2 till yn. And you want to choose one single point, vector a, which makes this error minimum. We did it in both lecture 1 and lecture 2. What do you set a to be? You have a bunch of points and you want to find one point which is in minimum aggregated distance from all of them. What is that point? Centroid, exactly. So we did it in clustering, right? When we wanted to do the clustering, the centroid of your data set was the point which was in minimum distance from everybody else, right? Again, in the maximum likelihood, when we wanted to just find out the average of the maximum of the Gaussian distribution, we found out that we need to just minimize the same expression, and then we ended up choosing the mean to be the centroid of the data that we have. And the centroid is simply the numerical, the arithmetic average of all the points, right? So if I wanted to solve this problem in terms of A, then the solution is simply this guy, right? So the best A that I can choose, which is in minimum distance from all y points that I have, is the centroid of y, right? Correct? Now, what is this A? We defined it here at the top, so you look at it here in this expression. A is A times mu, right? And y is the same A times xn, correct? So what I can say A times mu, which is A star, this is the optimal A that I have, is being the average of all of those y's, which is A times xn, correct? So A doesn't play any role here, right? So I can just get rid of A from both sides, and then I can set mu star to be exactly the center point. Meaning that, I mean, this is quite intuitive for you. So if you want to find the right bias, you just look where your data lies, and then you find the center of your data. That is going to be the center or the bias of your model. And then when you want to just compute the latent space, what should you do? You get the data, you subtract it from the bias. Take that one, just push it towards the center, right? You put the bias exactly on the center, now you got rid of mu. So this is x minus mu, right? And now you multiply it with your matrix U. So same thing as we did here. So maybe your data is not in this ellipse which is centered at the center, but this is somewhere here, right? And then I look at the center of that ellipse, I just shift it here, so I put it at the center, and now I start to just multiply with one matrix mu. Everybody's clear? Any questions? So, moral of the story, the bias is simply the centroid of your data. This is the best thing you can do. Yeah? So no need to just go through gradient and other things. I mean, if you compute the gradient with respect to mu of j and then you set it to 0, then it's going to be the same thing. You're going to end up with the same conclusion. Okay? Now, the next thing that I have is now I want to just specify this matrix mu. So matrix U, because I do have mu, and then I just want to find out how I should set this matrix U. Then my whole problem is over. So how can I do it? Let me first define something which is the error for sample n. So what is the error? The error is basically your reconstructed version minus your original version, but I'm not computing any norm on it. I mean, basically the distortion that I defined, the risk that I defined, was the summation of the norm of these error terms over all the data set, right? So, yeah.
Why would it not be the other way around?
That doesn't change anything.
Oh, because like, wouldn't error be negative in this case, but if you left it?
It's okay. I mean, it depends on how you think. I mean, it could be positive or negative in both cases, right?
Oh, could the reconstruction be larger than the original?
Yeah, it could be. I mean, first of all, they are vectors, right?
Yeah.
But so mean the terms, right? Because when it's a vector, it doesn't really mean which one is larger or smaller, right? But it could be up or down. Yeah, that could happen, right? So if you have a line, you're projecting everything on the line. Some of the data points would be under the line. Some of the data points would be above the line, right? Yeah. So it doesn't really matter. If you define it that way, it doesn't impact anything. Okay? At the end of the day, you compute the norm, right? And then that is the same. So now let me define this this error term to be this one. And if I define it, the thing that I want to compute is the inner product of this error with this particular term, x hat n minus mu. And what is this one? This is my reconstruction unbiased. Okay? You might wonder why I'm doing this, because if I can show this guy is 0, then I conclude that this vector E is orthogonal to this other vector. Yeah? So this is the whole purpose that I'm looking for. Okay? So to just keep the derivation simple or quick, so I'm going to skip a few things. So you do have all the derivation here. You can just try. It's just a practice of matrix vector product. But once you do it, at the end of the day, you just use the feature that U transpose U is the identity matrix. And at the end of the day, you're going to conclude that this phi term phi n, is going to be 0. Okay? Meaning that if you have your reconstruction, so say this is your reconstruction, this is your true data, the error, which is the distance between these two, is orthogonal to your unbiased reconstruction. So a better representation is this one. Okay? Look at this diagram here. So this mu star is the point which is the bias, right? So we shifted everything to that point. So we put our origin there, right? So once I am at this point, this x hat minus mu star is basically my reconstruction starting from the bias, right? And then the original point xn is in a distance from that mu star, and the error term is orthogonal to the other one. Does it make sense? It makes sense. I mean, it's a kind of principle. We call it the principle of orthogonality. If your estimation is very good, then the error of your estimation should be orthogonal to the estimation that you have. Okay? So, moral of the story, En, which is the error that you get, the error vector, that guy is orthogonal to your reconstruction. And what can I say? I can simply say that the blue line, the blue vector squared plus error vector, the red vector squared, is going to be the black vector squared, right? Everybody agrees? So, meaning that this En, this term, squared, the norm, I mean, when it's in a high dimensional or any more than one dimensional space, then it's going to be norm. So it's going to be norm squared plus the norm squared. This is the blue term here. The blue vector here. And then this guy is the other black vector that we have, right? So the orthogonality gives us this conclusion that our error term plus our estimation norm is going to be the norm of the true data. Okay, everybody's clear? So why do I need that? Because now I can simplify everything much better. So first of all, if I compute this particular, norm, this one, it's quite easy. Again, you can just try it by simple practice of vector matrix product. You're going to see that this term, you basically don't need to practice anything. Here is x hat minus mu, and what we do know, x hat is uz plus mu, so if I take this mu the other side, it's uz, right? And u contains bases, right? As I told you, if you multiply anything with a base, it's not going to change the norm, right? Meaning that the norm of uz is going to be norm of z itself, right? So that blue vector I showed you is the norm of your latent representation, yeah? And what you can do, you can write it down here instead of that term. So now what I conclude is that this guy, which is the norm of the latent representation, plus the norm of the error equals to, let's get back here, so it was here xn minus mu, right? Now, xn is the data point, correct? Is a sample. And mu was the centroid of the samples. Does any of them depend on you? If I give you the data points, you can compute xn and mu star. You can compute that distance, right? Meaning that this guy, whatever it is, it's going to be constant in terms of you. It doesn't depend on you. Moral of the story, if you add up everything in terms of n, then summation of these ENs squared are going to be your distortion, your J term. Because if you remember, your J was, okay, I don't have it here. So my J was 1 over n summation norm of x hat n minus xn, right? And I defined it to be En, right? Now, summation of norms of En is your distortion, correct? So this guy is the distortion, you see, if I sum it up over n, and this guy is another term which is only depending on your z, correct? And this is going to be something constant. Or in other words, I can say that my reconstruction error is simply some constant minus that average of norms of my latent representations. So now, if I want to minimize J, what can I do instead of that? Any clue? Any idea? I want to compute and minimize J, right? I do know that J is some constant, so this guy is now some constant, minus some other term. Yeah, so let me just write it down VAR right now. Okay? Now, if I want to minimize J, and I don't want to deal with J, what can I deal instead with? VAR. Yeah, exactly. And this is minus, right? So I'm going to maximize it, right? So if I maximize this term, it's exactly the same as minimizing J. Everybody's clear? So this is something that when you open up any textbook, they usually start with this one. So they say they don't say that we want to do representation error minimization. They basically say that we want to just maximize the variance of the representation or the variance of the latent space. And what is the variance of the latent space? This term that I showed here. The average of Zn squared. And why we need to maximize it, because when we maximize it, we are essentially minimizing the representation error. Yeah? So at least for me, if I just open up that one without any background, it's not totally clear. Unless you have a bit of a statistical background, right? But once you look at it from a representation error point of view, then it's going to make sense, right? So if you maximize this variance term, this term 1 over n summation, If you maximize it, you essentially minimize the representation error. And this is what you want to do, right? Okay, so one question that you might have is that why do we call it the variance? So that is quite, I mean, it's just an intuitive illustration. Mu star, we talked about this. This mu star is basically the centroid, right? It's the average of all the points inside your data set. So what you have a transformed or projected version of your data points, and you are just subtracting it from your projected mean, right? So you can look at this U transpose time mu star as your data set. So every single point inside your data set is first projected, so I'm writing it down as U transpose times the whole data set, meaning that I get every single data point inside data set and transform it, just project it by U transpose. Now I have this guy. This 1 over n summation of those points is basically the average, the arithmetic average of that. And then every single Zn is my projected point minus the mean. And if I average that one, this is the definition of the variance. So it's nothing specific here going on. Just wanted to show you that this is basically somehow proportional to the variance of your representation. Okay? This is why people call it the variance, but this is not it's not something very sophisticated. It's just intuitive illustration. Okay, so the whole problem that we want to do is to just do variance maximization, and I hope that after going through all of those, tiring analysis, you got the idea that it makes sense. But if you somehow got confused at some point, please just stop thinking about that and start from this point. Okay, the whole thing that I want to do is to just maximize this term that I have here, that summation over Zn's, right? Okay, I do understand that it could be a bit, especially if you have not refreshed your mind about the linear algebra, it could be a bit of too much computation, but you can do it again later when you have time, okay? But the moral of the story, I just want to maximize this term. And this is the whole, eigenvalue, eigenvectors that are going to show up right now, okay? Everybody's clear what I'm going to do? Right? So, what I'm going to do, I do have my data set. I just shift everything to the origin. So this is down biasing, so subtracted from mu star. Everything is now around the center. And now the next thing that I want to do, I want to just find U such that when I multiply U transpose to all of these data points after shifting them to the origin, the variance of what I get out of this transform is maximized. Why? Because if I do that, then I know that my error is minimized, right? Okay. Now, it's going to be a bit tiring if I just start with a general U. So what I do now, I'm going to get back to the examples that we had. I'm going to start with one single one, okay? So I'm assuming that I have just one dimension. K is exactly 1. So when K is 1, then U is going to be, this matrix U is going to be simply a vector. So it's going to be a vector U, which is d-dimensional, and my Z, which is now a number, because my latent space contains only one variable, one entry. That guy is going to be inner product of U with my shifted data point, right? Everybody's clear what I'm doing? So in this case, I'm computing just one Z, and then every single point I just shift it to the origin. Now I multiply it with vector U, right? And then I get one number. And if you open it up, so it's going to be this term, and I just do the summation, so you can just replace it. And now I'm going to write it down in this form, okay? And now this is the important part. Please just pay attention. Just make sure that you understand what I'm doing here. So what is this X tilde here? X tilde is the whole matrix of data which is shifted. You see it? So the first column of this X tilde is my first data point x1 minus the bias, right? The second one is the second data point minus the bias, and so on till the last one. How many columns do I have? number of data points that I do have. How many rows do I have? Every single x is in d-dimensional space, right? So it's going to be a d-dimensional vector, right? So I have d different rows and different columns. Clear? So this is my data set which has been unbiased. I got every single point, shifted to the origin, and then put them next to each other. Clear? And this is d times n dimensional. Okay? Now, if you multiply this u to every single of them, it's basically the same thing as multiplying u to that matrix and then compute the norm of the output. Do you agree or not? Yeah? Yes?
Sorry, I'm just confused. Why is U equals bias?
Sorry, what is bias?
Like, are you not representing like the lowercase u as bias? Or am I saying that?
Lowercase u is not the bias, no. That u is your vector, the transform. Because it's the same as matrix u, but now your matrix has one column.
Oh. And you're just calling u, lowercase u, equal to the first column of it, right?
Yes, exactly. Yeah. This is only one column. Yeah. You don't have more than that.
But isn't that equal to just u equals u substance, like u1 then? Because it's the first column of u?
Yes, but I imagine that k is 1. Yeah. I mean, sorry for that. Maybe it's another very good notation. Yeah, it's u1 exactly.
Basically,
But I don't have u2 anymore.
Yeah.
Yeah, it's just u1. Yeah, you're right. Sorry for that. Yeah.
Oh, okay.
Yeah. So it's just one column. So your whole matrix u is just one vector u. Okay? So, okay, in the first line, so u, the capital U is exactly your vector u. Okay? Okay. Now, do you agree that if I multiply U transpose to this matrix and then compute the norm, I'm going to get the same thing as the summation above? What's going to happen when I do the inner product? So maybe I do it here for you. It's important to see it because then you cannot follow anything. So my x tilde is x1 minus mu, x2 minus mu, and so on till xn minus mu. Right? This is my x tilde, correct? This guy is the matrix x tilde, correct? Now, I am multiplying U transpose to this guy. So I am getting U transpose multiplied to this guy. What's going to happen? This U transpose is going to get multiplied with this one till the last one, right? Correct? So this is going to be the same as I multiply U transpose with the first column, U transpose with the second column, and so on till U transpose to the last column. Correct? Now, what is this guy now? This is U transpose x tilde, and is it a vector or a matrix? What is it? If I multiply, if I compute the inner product of U with a column, what comes out of it? What number, right? So every single inner product here is one single number, right? So now, is it a vector or a matrix? It's a vector, right? Now, if you compute the norm of this vector, what's going to be? It's going to be the first term squared plus second term squared and so on, right? So the norm of this guy, norm of U transpose x tilde, it is going to be summation of n from 1 to n, U transpose xn minus mu, right? Squared. And this is exactly the summation we have in the slide, correct? Everybody sees that? Yes or no? Yeah? Everybody's happy? Great. So what I am writing down now, I'm writing down my whole variance that I have and I want to maximize. I can write it down in terms of this norm, okay? And now, let me just go ahead one step further. If you have one vector, okay? If you have one vector and you want to compute its norm, can I just multiply it with, or compute the inner product of the vector with itself? Is it correct or not? Please? I want to compute the norm of something, say some vector A. Can I write it down A transpose times A? Is it correct? Yes? Everybody agrees? Yes? Okay, so now instead of A, I have this vector U transpose times X tilde. Okay? And if I want to compute the norm, I can write it down U transpose X tilde transpose X tilde transpose times U. You see that? So this is the vector itself. The transpose version of it is going to be X transpose U, right? A B transpose is B transpose A transpose, right? So it's going to be U transpose X tilde transpose U, correct? Now, this is what I'm going to do. And I'm going to open it up in this form. So my summation that I'm looking for is simply U transpose times that term in between times U, right? You see it here. And now one thing that I'm going to define is the sample matrix, sample covariance matrix, and that is simply this 1 over n times X tilde transpose. Okay? Now, first of all, what is the dimension of this guy? And you take a few seconds to think about it. Look at this X tilde. How many rows do you have? D. How many columns do you have? N, right? And then if you multiply it with its own transpose, it's going to be D by D, okay? So D N multiplied with the transpose, which is N, D is going to be D by D, okay? Now, this is the covariance matrix, and if you understand what I'm trying to say right now about the covariance matrix, then you get the whole idea of PCA. So, what is special about this covariance matrix? Let's first try it for some data and see whether you do understand what is happening with this covariance matrix. Okay, this is the sample covariance matrix. So I said I get my whole data set. I write it down in the form of X tilde. I compute X tilde transpose, and then I divide it by n. So let me just write it down for one specific case. So look at this initial example we had, and say that my data points are all on this line x1 equal by x2. You remember that example, right? So every single data point that you have is lying on this line. Clear? Okay? Now, if it could be potentially not here, it could be that my data set has only values here, right? But if then I do the unbiasing, what do? I'm going to find the middle point and then shift everything to the origin, right? So at the end of the day, I'm going to always have the same number of points here and same number of points here, right? Everybody's clear? Right? So this is going to be my data set, and say this point is minus 2. So this is again minus 2, minus 1, minus 1. Oh, sorry, this is not. Minus 3. Minus 3, minus 2, minus 2, minus 1, minus 1, 0, 0, and so on. Okay? If I want to make my x tilde, can you tell me what is the x tilde? Now let me just forget about this minus 3, right? Okay? I have just these points. What are the points inside that? What is the first unbiased point? Starting from here. Minus 2, right? So my x tilde is going to be minus 2, minus 2. Okay? What is the second one? Minus 1, right? Next one is in the center, right? 0, 0. Next one, 1, 1. Next one, 2, 2, right? This is going to be your x tilde. Now, if I get this one, what is the dimension of this one, first of all? It's 2 by 5, right? 5 is the number of data points that I have. 1, 2, 3, 4, 5. And 2 is the dimension of my data space. Every single point is in 2 dimensions, right? If I get this guy and multiply x tilde with its own transpose, what would be the dimension of this matrix? What is it? 2 by 2, great. So can you compute the first term for me? This guy multiplied with itself, it's 10. I did the computation. It's 10, okay? What about this guy? This is going to be this one multiplied with this one. It's again 10. This is 10, this is 10, okay? Everybody's 10. Everybody's clear? You got the idea how I computed the sample covariance? I mean, of course, I had to just divide it by number of points, which is 1 by 5, but I don't do it because I don't want to have too much fractions. Okay? Now, if you look at this matrix, you can decompose it using its eigenvectors and eigenvalues. And I did it before, and it's going to be this one. So, look at it. The first column in the first matrix is one eigenvector, and the second one is the second eigenvector. Do you agree or not? I did this example for you when I started talking about the basis. Right? If you get the first column, just look at the very first matrix. If I multiply the first column with the second column, what's going to be the output? The inner product of the two columns? It's 0. 1 over square root of 2 times minus 1 over square root of 2 is minus half. The second product is going to be half, minus half plus half is going to be 0. Clear? So they are bases, right? So these are the two eigenvectors, these two guys. And then exactly the same thing transpose is the last matrix. And the middle one is the matrix of, what are inside the middle matrix? Eigenvalues. So what are your eigenvalues? Can you tell me? 20 and 0. Great, right? And 20 corresponds to which eigenvector? The first column, right? 1 over square root of 2, 1 over square root of 2. Great. So now that you see this, let me just go ahead and draw them for you. So the blue one is the one which has eigenvalue 20. The red one is the eigenvector whose eigenvalue is 0. What do you conclude out of that? Great. So your data is somehow distributed in the direction of the one which is non-zero in eigenvalue, right? The one whose eigenvalue is 0, that 0 eigenvalue basically tells you that your data has no spread in that direction, right? So if I compute the decomposition of the covariance matrix, which is exactly this base, you see the red, green base, then one direction is giving me the direction, the one with higher eigenvalue, non-zero eigenvalue, is showing the direction where the data is spread, and the other one is showing me the direction whose eigenvalue is 0, and that 0 eigenvalue basically tells me there is no spread in this direction. Now, if you wanted to choose U for this particular data set, what do you choose as U? That vector U. the vector which you get it, and every single point that you have, you project it on that one. Which one do you choose? The blue one, right? You're going to choose blue one because that blue one is 1 over square root of 2, 1 over square root of 2, right? And every single point that you have inside your data set is a product of this kind of vector, right? So this is the right choice. This blue vector is the right choice of the direction that you want. And this is the kind of property your sample covariance has. Now, in practice, you are not going to have exactly everything on the line, but you could have them spread, right? But once you compute again the sample covariance, you're going to get two directions. One of them is the blue one, one of them is the red one, and although it's not observable from here, but I have written about the blue one, the one which contains the higher eigenvalue, and the red direction is the one whose corresponding eigenvalue is smaller, right? Now, if in this case you wanted to choose one direction, which direction do you choose? The blue direction again, right? Because your data is mainly spread in that direction. It's not a spread in the red direction. I mean, it's a spread in that direction, but not majorly, right? The major spread is in the direction of where your eigenvalue is larger. Clear? So you could show it, actually. I mean, if you go through this one, and I don't want to tire you anymore. If you are interested, you can follow it up at home. But you can, at the end of the day, see that if you want to maximize this variance term that I told you, you basically need to set that u to be exactly the eigenvector v. So in this form, you need to exactly put, okay, these are a bunch of blah blahs. So you need to exactly put u to the eigenvector v max, which contains the maximum eigenvalue. Okay? So, moral of the story, you have your data set, you compute the sample covariance. Once you have the sample covariance, you find out all the eigenvectors, right? And then you look for the one which is the highest eigenvalue. That is the direction where your data is most spread. And if you want one direction only, this is the only direction that you should go for. Everybody's clear? Everybody got the idea? Can I sleep properly at home tonight? Or it's just, I just made it more confusing for you? Huh? Okay, so I hope that you got it properly, fine enough, because I tried my best. But I mean, I do agree that this is not the best or the easiest thing to study at 8:30 p.m. I do agree. Okay? But I mean, I hope that, I mean, if there is anything confusing, you might look at it at home. But I hope I could transfer this idea to you, that when you look at your data, you can construct that covariance matrix, and that one is going to describe you where your data is spread. And once you have that spread, then you basically go to the direction which is most spread, right? Now, what if I want to have two directions now instead of one direction? I told you that my latent space is just one number initially, right? But what if I do it for k equal by 2? What's going to happen? Any suggestion? Don't look at the equations here. Sorry? Keep two columns. And what are those two columns? Don't be shy. I mean, you are doing a great job. Exactly. Great. So, as your friend said, like if you have two, again, you're going to write it down in this form. So, sample covariance is going to show up in both terms. So, you have U1, U2 right here, right? You want to choose those U1 and U2. What should you do? You're going to go to the sample covariance to find all the eigenvectors. And then the first one, the one with largest eigenvalue, is telling you the most spread direction, right? The second one is telling you the second most spread direction, and so on, right? So you're going to go and choose the one. U1 going to be Vmax1, and Vmax1 is the one which has largest eigenvalue. And then for U2, you're going to choose Vmax2, which is going to be the second largest eigenvalue, right? Now, if you want to do it for k different directions, what you would do? You're going to just go and do the computation, and after that, you just go for the first largest eigenvalue, second largest, third largest, till k largest, right? So, that is going to be the algorithm which we call it PCA, principal component analysis. Because once you compute your covariance matrix, those eigenvalues are the principal components of your data set. And if you just want to show with k different directions, then you're going to get the k largest ones, right? The k dominant ones. And then that's it. So once you have your data set, you start with computing the average. So this is going to be your bias. Then you shift everything to the bias point. So everything gets back to the origin. And now you're able to compute your covariance matrix. Once you computed your sample covariance, then you just sort out all the eigenvalues. And you start from the largest one. And you take that direction, the direction of the eigenvector, and you keep on going till k is over, right? And then if you do that, you essentially have solved the original problem optimally. So there is no iteration, nothing like that here. Okay? We have the optimal solution. Everybody's clear? Any questions? No questions? Great. So if you got no question, then let's get back to the original story we had. So about the application. So one of the things that I told you was the compression, right? And when we started, I told you, like, for instance, we want to compress the image. So how can we do this? So eventually, I mean, we talked about that this image is a 60K dimensional vector, right? And then you can just drop it to a lower dimension, right? But if you want to really do it, so if you just want to think of this whole image as one vector, one data sample, then you need, if you want to compute that covariance matrix, you need to have a lot of samples, right? Meaning that I mean, here is 60K, correct? So the dimension is 60K. If I really want to just make that sigma, the covariance matrix, in principle, I need even more than 60K, right? So I need to collect even more than 60K different images of a person, grayscale, right? But this is not a good idea. A better idea is that, what we do in practice is that we think of the image itself to be a part of data set, right? So your image, I told you, it is 200 by 300, right? 300 rows, 200 columns, right? So I can think of it as 200 different samples, right? Each column is one sample. And then that guy is of dimension 300, yeah? And then I can just apply PCA on that data set. So meaning that I compute the covariance matrix, and then I just try to find the K principal components, and then I just project everything into that subspace. So if I do that, then it's going to work eventually, and you can do it at home. So if you are interested, just search online, doing PCA for image compression. It's going to work. And here is from one old repository I found online. So if you set K equal by 0, then your compression going to look like this. So what I am doing here, I am doing the K-means, PCA, so to compress. And once I have compressed, then I take it back to the data space. So I reconstruct. So I find that U, I multiply everything to the U, then I get the lower dimension, or U transpose, sorry, and then again get the lower dimension, the latent space, multiply it with U once again, and I get the original image. So if I do with K equal by 0, I'm going to end up with this. But what does K equal by 0 mean? What do I have? Do I have any matrix U? No. The only thing that I have is bias, right? So I just centered everything. I have pretty much done nothing, right? So I have only centered the data, and then that's it. And then whenever I want to recover, for every single data point inside my data set, I just take the center, which is, of course, something relevant. So what you see here is basically the average of every single column. That's it. Yeah? But what if I increase K? Then it's going to somehow improve in resolution. So here K is 10, meaning that every of those columns which have 300 pixels, I am going to drop it into 10 different pixels. keep it, and whenever I want to reconstruct, I multiply those 10 pixels into matrix U, and then I get back to the original image. Yeah? And if you start to increase k, you're going to see that it's getting better and better. Okay? So this is k equal by 50, which is roughly, it's very close to the original one. And you essentially don't need all of those 300 different pixels in each column. You just need 50 of them to have a very good reconstruction. Okay? So it practically works, really. It's not just a bunch of boring linear algebra things. Okay? So this is one point, but compression is not the only or the major application. One of the major applications that this idea has is the idea of face recognition. And what is the question of face recognition? You have image of lots of people, right? And then the thing that you want is that if I show you one new image, you want to tell me whether it is related to anyone inside your data set or not. And you do have lots of applications for that in mind, right? So if you want to just recognize whether someone had been here before or not, you just look at the image that you take from that guy, and then you want to compare it with the images you have inside your data set, right? But this is not going to be very efficient if you just get the image itself and compare it to the other image. Because when I look forward, I have some pixels, but once I just change my direction, or if I change my gesture, it's going to change. All the pixels are going to change, right? So it's going to be different. One of the key ideas that helped us doing this was this PCA. And the idea was that I start with this image, which is in very high dimension, and then I try to compute the principal component of that one, which is in a very low dimension. So I find a very small latent representation. So what is the key factor about that latent representation? Is that that latent representation contains the key factors of my face, right? So the shape of my eyes, my nose, my mouth, my hair, everything is somehow captured on those few latent properties, right? Latent representation. And if I had that one, if you take any other photo of me, which could be totally different in pixel, once I do the same compression, I'm going to end up with a very close latent representation, right? Because the key features of my face are not changing. It's only the direction and gesture that is getting changed. So if you want, this is the key idea. So you find some k, which is not eventually very large. So usually you are doing it less than 10% or something like that. And once you do that, then you simply get the image. You do the projection into a lower dimension. And whatever new image you get, you compute the same latent space and you compare the latent spaces. Okay? So the latent space representations. And if they are very similar, then they are going to be, or we do consider them to be the same person. For instance, just consider these images. So these are, both of them are the same person, but in each of them, she has different gesture, right? And then if you just compare the pixels of this one could be essentially very different from this one, right? But if you do a very low dimensional latent representation, both of them could end up with a very close representation. And now you say that the same representation, which we sometimes call it the eigenface, of this image is same as eigenface of one other image inside our data set. So that person had been before here. You got the idea? So this is the idea of face recognition. It really works. I mean, the accuracy is somewhere around 80% if you do it properly with fine value of k. But then you need to just fine-tune k, right? So you need to try it for different choices of k and just evaluate the generalization error. The same story we had last time, right? So you validate it, and once the validation is okay, you just check the generalization, that's it. But it really works. I mean, if you're interested, you can try it at home. Yeah? And I'm going to just put you some simple exercise in the next assignment that you try PCA and this stuff, okay? Okay. One other application is the application of matrix completion. And the idea of matrix completion is probably, I mean, I'm pretty sure all of you have seen it. like in the recommendation systems, right? So for instance, say this is, I don't know, some Netflix or something web page, and then you have different people, and every person has seen some of the movies, right? Not all of them. And then after seeing that movie, he or she has rated that movie. So you do know, for instance, that this person has seen this is Fight Club, right? So has seen the Fight Club and rated as 4, has seen this one, which is a animation, and rated as 1. And what you want to know is that what would be the rating of this guy for the other movies, right? Which he has not seen yet. And why you want this? Because, for instance, when you open Netflix, it's going to suggest you, recommend you that, because you have seen this movie, so maybe you are interested in that one, okay? So now, the question is how you can find these missing points inside your rating matrix. And again, you can't look at it as a PCA problem. How you can think of it, you could say, let's say I have one specific user, and that user, I have lots of movies inside my portal, right? And for each of them, in the ideal case, this person could just give me some rating, right? But he's not giving all of them. He's just giving a few of them, right? So this is the D-dimensional thing, which is the D different movies you have and the rating of person for every single of them, but you don't have all of them. But one thing that could be, which is eventually the case, is that you can write it down in terms of the superposition of some few principal components. So there exists some specific pattern of rating between people. So some people are interested in comedies, some people are interested in, documentary, animation. Everybody has a specific behavior, but those kind of behaviors are much, much less than the number of movies you have on a portal like Netflix, right? And then if you do know that those eigenbehaviors, those U vectors, then everybody who is rating is going to do a superposition of those ratings, right? So I am interested, for instance, comedy and documentary. So it's going to be the superposition of those two with some weights, right? So what you can say that there exists some sort of eigen ratings. So some specific ratings which are for a society the community that you are studying, and then any rating in that set, that data set, you can represent it basically in form of superposition of those eigen ratings. And this is again something like PCA, right? So you don't really need to know the rating of every single movie for the person. You do need to know the latent representation of his rating. And once you know that, since you do know the eigen ratings, then his ratings is going to be that superposition. Okay? So this is, for instance, what all of those recommendation systems work based on. So for instance, you are using Amazon website or any other online shop, they are basically doing the same thing. So they have a very big data set. Once you rate, they're going to collect that as information, and based on that one, they're going to solve some sort of PCA-like problem to find out what is the eigen ratings for this community, right? And out of that, they are going to just find out what are the missing rating for you. And once they know that, they just recommend you the ones which are high in your rating after solving the PCA problem, okay? So this is what is happening in practice, and one nice story about that is that some people the people who just solved this problem in form of PCA, they were working on the Netflix challenge in 2009, and they could win this $1 million prize for that, which was that, they wanted to just design a recommendation system, and they ended up looking at it as something like PCA, and then they tried to solve it by that one. There is a bit of more sophistication to that, but the principle is the same thing, And then it's pretty much how most of those recommendation systems work nowadays based on, because they are linear and very efficient in computation. So that's it pretty much about the PCA. There are only 2 points that I want to mention just as a kind of goodbye to the whole thing. So the first one is that your PCA algorithm is very sensitive to scaling. Meaning that if one of my axes get a scale, just look at this guy, right? So if I get this guy and then look at this data set is more spread in horizontal axis, right? If you want to choose one principal component, you are going to choose the horizontal one, right? But if you scale it back, something like this happens. It might be, for instance, you just computed all the heights in centimeters, but then you scale it to meter. Then it's going to change in a spread, right? It could be smaller. And then the spread changes, the eigenvalues change, the principal component could change, right? So this is a very crucial thing in PCA. PCA is very sensitive to scaling, and one of the solutions that we have is that we always normalize data to some reference that we just agree on that before we just process the data in PCA. Because if we don't do that, then we could just simply end up with wrong conclusion, right? So we just find the wrong direction as the principal component, even though it's not. So this is one point. And the other point is that PCA is linear, right? So if you look at these points on the circle, can I show every single point with one variable? I can. Why can't I can? If I do know the angle, I can show it, right? Am I correct? So every single point is on one circle, right? The moment that I know the angle, I know what the point is, right? But I cannot do it with PCA, correct? Because PCA only can draw lines. It's a linear approach. So if I could have a nonlinear PCA, then I can again show this data set with only one latent representation. And this is the idea that we build autoencoders with. Yeah, so if you have the deep learning course, it's going to be the chapter 8. And there we again start with PCA. Yeah? So autoencoder is basically PCA, which is nonlinear. So it tries to just draw those directions. They are not linear anymore. There are some sort of nonlinear surfaces. Okay? So that's it for today. These are the references you can check. So Bishop is the best one. Also, you might take a look at Goodfellow for the overview on linear algebra. So he has done a good job. So if you want to just recap your linear algebra again. We are over with unsupervised clustering, data distribution, distribution learning, and dimensionality reduction. Good news is that we're not getting back here, okay? And it's going to be much conventional, okay? So the next thing that we are going to do is supervised learning, and we are going to start with linear regression, which is the nicest thing you can think of. So next week, hopefully, is a very charming lecture, okay? See you next week.